Let's go through this example problem where we apply the relations between thermodynamic properties to a strip of stretching rubber. So the problem statement says that we're interested in the thermodynamic properties of a strip of rubber as it's stretched. Consider n moles of pure ethylene propylene rubber that has an unstretched length z0. If it is stretched by applying a force F, it will obtain an equilibrium length z given by the expression shown, where K is a positive constant. And they also give us the heat capacity of unstretched EPR. So the first thing we have to do in part A is come up with fundamental property relations for du and dA for the system, where A is the Helmholtz energy. And we're also given an expression for the work required for a reversible elastic extension. So the first thing I'm going to do is go ahead and draw a schematic of the situation. So in part A of this problem, it's asking us to find expressions for du and dA. The first thing we're going to do is write the first law of thermodynamics for a reversible process. This equation is given by equation 5.6 in the text. So this right here is equation 5.6 in the textbook. And it's important to notice that the dq term right here correlates to the TDS, and this plus dW reverse is equal to negative PdV right here. So we're already given an expression for dW reverse from the problem statement. So what we can do now is just plug in this expression that we have here for this entire term right here. And this is our final expression for du in part A. So now we're going to try to find an expression for dA. So the first thing we're going to do is start off with the definition of Helmholtz energy. Now I'm going to take the derivative of each term. Now I'm going to expand the dTs term using the total differential. Now from this expression, I'm going to plug in the expression for du that we already calculated up here. So from here we can cancel out the TDS terms and simplify. And this is our final expression for dA. Now for part B. So part B says, develop an expression that relates the change in entropy to the changes in temperature and length. So what we need to do is start with S is a function of T and Z and find ds so that we can get the expression in the form of those differentials and also the constants A, B, K, N, and Z0. So I'm going to start from this expression right here, that S is a function of T and Z. From here I'm going to take the total differential. So now we have this total differential. The first thing that I'm going to do is figure out an expression for this term right here, the ds over dt at constant z. So the first thing that I'm going to do here to find this expression for this right here is to write out the molar heat capacity expression that they gave us in the problem statement. So this heat capacity expression is on a molar basis, so I'm going to multiply by n, the total number of moles. So now that we have this expression right here, the next thing that we're going to do is plug in the equation for delta U that we found in part A right here and simplify the expression. So with this simplified expression right here, we have the change of z over the change of t at constant z. So this is just going to cancel out and go to 0. So what we're left with is this. So now if I divide this t over to the other side, we can get this expression from up here of ds over dt at constant z explicitly. So this final expression for ds dt at constant z can be plugged in up here once we figure out the rest of this expression. So the next thing I'm going to try to solve is to find an expression for ds over dz at constant t. So what I'm going to start with here is the expression for dA that we calculated in part A. And this expression right here is a fundamental grouping between A, Z, and T. So this right here from the textbook just means that the three variables are in a fundamental grouping, and since they're in a fundamental grouping, we can express them as a Maxwell relation similar to what is shown in equation 5.15 in the text. So this is the Maxwell relation between these three variables. So next what I'm going to do is solve for this term right here and this term right here. So the first one, dA over dt at constant z. So I'm going to simplify this by plugging in the expression for dA that we calculated in part A. And I'm going to simplify this equation one more time. So at this expression, delta z over delta t at constant z is going to go to 0, and dt over dt at constant z is equal to 1. So this equation reduces to negative s. So now I'm going to do the same thing for dA over dt at constant t. After doing the same thing to dA over dz at constant t, we get that this expression is just equal to f. So if we plug in the results of these two expressions right here back into their respective parts in the Maxwell relation, we will get the following equation. So right now we have an expression for ds over dz at constant t, and that's what we were looking for this equation up here, ds over dz at constant t. So we're going to continue to simplify this expression until we get it in terms of the constants. And so the first thing we're going to do is plug in the expression for f from the diagram that we have. So f is equal to kt times z minus z0. So we're going to plug that in for f in this partial derivative. So let's take the partial derivative of this expression with respect to t, and it's just k times z minus z0. So this right here is our final expression for ds over dz at constant t. And at this point we can plug in this and what we calculated earlier up here for ds over dt at constant z into this expression ds that we have. So we already solved for this and we solved for that. So now all we have are constants and the differential of temperature and length. So we can go ahead and plug that in and get our final expression for ds. So this is our final answer for part B. Now for part C, it asks us to develop an expression that relates the change in internal energy to the changes in temperature and length. So basically we're going to do what we did last time for S except with U. So we're going to start with U as a function of T and Z, and we're going to find an expression for du. So the first thing we do is take the total differential. So what we need to do here, just like in part B, we need to solve the expressions right here, these two, du over dt at constant z and du over dz at constant t. So if you remember from part B, we already solved this expression right here, and it's equal to n times a plus bt. So for du over dz at constant t, we need to plug in our expression for du and simplify the equation. So after simplifying, you get this expression right here, and we can simplify this because this is going to go to 1. And the next thing we're going to do is, so we already solved for ds dz at constant t, So we have that expression in terms of K, Z, and Z0. And we know what F is from the schematic where it gave us what the force is. So I'm going to plug those expressions into this simplified equation right here. So once you plug everything in, you'll notice that this actually cancels out to 0, because you'll get KT times the difference in Z and Z0 minus KT times the difference in Z and Z0. So all this goes to 0. So what you're left with is that du is equal to solely n times a plus bt times dt. And that's your final answer. So that's the answer for part C. So for part D, it says, consider the relative energetic and entropic contributions to the isothermal extension of the EPR. So it gives you an expression for the energetic force and the entropic force, and it wants us to find expressions for F sub U and F sub S. So what we're going to do is plug in the expressions we've already calculated in parts of this problem for du over dz and for ds over dz in this part and this part. So this is the expression for F sub U. So we've already calculated that up here, and it was equal to 0. So the final answer is that F sub U is equal to 0. Now for F sub S. So they gave us this expression for F sub S. We already calculated ds over dz at constant t earlier, and so let's plug that in. We can then simplify this equation and get our final answer. So these are our final answers for part D. So now for the last part, for part E, it asks if the change from the unstretched state to the stretched state above occur adiabatically, would the temperature of the EPR go up, stay the same, or go down? So intuitively we can already answer that question, that the temperature would increase, but we can also back this up with the first law. So if you read out the first law, it said the stretching would be adiabatic, so there would be no Q, and in the process of stretching, the stretching is doing work on the piece of rubber. So when the rubber is stretched, that's doing work, the work term would be positive, therefore the change in internal energy must be positive. And to account for the positive change in internal energy, the temperature must go up. So the final answer is that the temperature would increase.